So let me start now. So that's a joint work with Haldun, Özgür, Bayındır, and Tasos Moulinos, who's here. It's about adjunction of roots with application to THH and K-theory. So maybe I'll start with a baby example that we all love. It's K-theory, topological K-theory. So the basic example here, this baby example was the Adams-Hammond, which for us will be a completed version of BP bucket 1 that maps to, let's say, P-completed topological K-theory. So we have the famous Adams splitting. In wedge Hammond of suspension of this Adams-Hammond. So you know that the coefficients, here's the periodics on this V1 class, and here it's the polynomial on the bot class. And we have this relation on homotopy groups. And we would like to say that, in fact, the spectrum Ku is obtained from the spectrum L by adjoining a root to V1. So on coefficients, of course, we have then this relation. Okay. So does this hold at the level of ring spectra in a sensible way? And if it does, can we then deduce? Let's say that we have computed THH, TC, K-theory of L. Can we then deduce it for Ku using such a relation? That we would have at the level, it's the other way around, sorry. Okay. And in fact, historically, it appears the other way around. We first computed THH, K-theory, and so on for L, and then for Ku, and then try to find the relation on how to work our way back to try and deduce it without computation. So what were these computations that we had? So let's just remind you very briefly. V1 is going to be the sphere mod P and V1, which has a V2 self-map, and the telescope is then denoted T2. Okay. And here, so there was McClure-Stoffeld. They computed V1 of THH. That was really at the very beginning of the THH story, actually. And they have a very nice one. That's a free commutative graded algebra. And then I did the computation for Ku. It was also kind of a painful computation, but I don't want to write out the answer because the answer is quite complicated and not very nice, okay? So I went I've been running around with this computation, complaining about that I didn't know how to deduce it from that one in a nice way. But then I was bugging Lars Hesselholt, and he told me, well, you have to use logarithmic THH, and it's going to be easy. So, fortunately, some other clever guys did this for us. So Sagave in 2014, he made sense of this formula. He gave the first, somehow, I think, nice construction of such a formula. So it's all P-completed here now. In commutative spectra, okay, as a commutative spectra, and then with Schlichtkrull and Rognes. So I think this is in 15 and 7 or 18, maybe they published. They have the complete log story. So Rognes had the first paper on logarithmic structure, and then with Schlichtkrull they developed it with a localization sequence, and then in the third paper they do it for KU. And then they prove a localization sequence. They say we have, what should replace localization sequence here should be something like this. And here somehow you don't want to take periodic Adams-Hammond because it wouldn't fit in a cofiber sequence, but you just allow the Keller differential on V1 to be divisible by V1 once in some sense. And they have the same formula for KU and KU. And then, well, they say the complicated computation for THH of KU just comes out of the formula that what is called now log-étal descent, THH log-étal descent. Okay, so that somehow really sheds light on how such a tamely ramified extension, as in the example of L to KU, is going to be reflected in THH. So first, when I started computing THH of KU, I thought this formula was true without the logarithmic part, and it took me a while to realize it was not. Okay, what about K-theory then? Well, in K-theory, somehow the output is, in some sense, even simpler. That's a theorem with Rognes. We had the first computation of V1 K of L. So here we have some, it's almost free. PV2 modules on 4P plus 4 generators. And then if we invert V2, then we have a very nice formula for the K-theory of KU, which is just again, it's all P-completed here, and formula like this. So it's in some sense simpler than this formula, but of course there's have to be careful that we have changed from the root of V1 to a root of minus V2. So that was somehow an example of what we call chromatic redshift. So not only is somehow the V1 periodicity of L and Ku transformed to a V2 periodicity of Kl and K of Ku, but also the root adjunction of a root adjunction of V1 is promoted to a root adjunction of V2 in some sense. And here also you can ask, can we make a spectrum level description of this kind of formula? So this was somehow these baby examples that motivate trying to develop more generally this notion of extension by adjoining a root to see what type of examples we have in nature of this phenomenon, and can we deduce also THH, TC, K-theory computation out of these examples. Okay. So let me now turn to these further constructions. So here we need to construct these root adjunctions, constructing root adjunction. So we learned from Hahn and Wilson the Hahn and Wilson annals paper that you have E2 polynomial algebra you want to see it as a polynomial algebra. That we can write like this. It's underlying E1 algebra. Its underlying E1 is the free E1 algebra on a sphere dimension K. Of course, here K is even. Okay. Sorry?
Didn't this appear earlier in Larry's paper on rotational invariance?
Yeah, sure. Yeah. In the rotation invariance of K-theory paper. I mean, it appears, I think, in various flavors.
Sorry, only in degree, only with generator in degree -2.
Yeah. Yes, and we have also we also have an E2 map. Like this, which on if you want to, is given by sending sigma km to sigma k to the m. So here you already guess how the root adjunction is coming into play. So the definition that we give with Özgür and Tasos so suppose given an E2 algebra and a map like this, right? Well, then from this formula you guess that we want to adjoin a root along this map now. M root. This is going to be just defined as A. Okay. So some remarks on this construction. So first, that's the most technical part maybe here. If A is an E2 algebra concentrated, let's say that the homotopy groups are concentrated in even degrees, and if K odd and A is a class even, sorry. Then you can produce such a map that will map sigma AK to A. Then exists. So here it should be MK, sorry. Yeah. But okay, so that's a technical, difficult part. We somehow we have to show that this is built out of even E2 cells. And then by some more or less obvious deduction from the fact that it's in even degrees, you can produce such a map, but it's I think in no way unique. So it's an abuse of notation somehow to say that if we take such a class, we take then such a map and we define this guy, right? So it's there's a choice. So I think it's somehow in some sense better to call A the map, but in fact, if you have an E2 ring spectrum concentrated in even degrees and such a class, you can produce such a map, and then you have at least one model of such a root adjunction. Okay. Well, then it starts looking a little bit like the example that we had above, because this guy is going to split. As shifted copies of A. And its homotopy groups are going to be given by the by the root adjunction. Okay. And from this splitting, you have actually a graded it inherits the structure of a Z mod M graded E1 algebra. Okay, so you have a graded object. So you have a E1 algebra in graded spectra, if you want, and at least you still have an algebra. Okay. So now, what can we say from this in THH and K-theory and so on? Bjørn was saying some people can immediately work these things. I'm not, as you see, I'm not. Okay. So, Antio. Mathieu, Moreau, and Nicolaus, Thomas. This was in 22, so that's in the paper on the Baylinson fiber square. They produce, they define a graded version of THH. And so essentially you take the cyclic bar construction in graded spectra, and if you have a graded spectrum and apply THH, you get a grading of THH. If you forget the grading, essentially you get THH of the algebra where you had forgotten the grading. So using a
Other people had done this before.
Yeah. Yeah, but maybe at least the equivalent. I mean, the S1 equivalent in the modern setting is probably appearing there first. Yeah. Many of these things have been around. I think in the various. It's not always so clear for me. So our first theorem, let's say in this setting. So now we put ourselves in a kind of tamely ramified version. We assume that. Oh yeah, I forgot to say something first. I don't want to carry this notation. So let's say that now, from now on, P is a chosen prime. And such a thing that I'll just write this for B. I've chosen extension, okay? Okay, so the theorem So again, P is prime to M. Yeah, then the induced map on THH. Splits. Identifying THH of A with the degree 0 part of THH of B. Okay, so this is the degree, homogeneous degree 0. Of this ZM graded spectrum. Okay, and the same holds for TC minus TP. And for example, on this kind of guys, okay? So I wanted to indicate a proof, maybe just to, if you are new to this kind of things, maybe you are wondering. I wanted somehow to highlight where this comes from, why we have this condition here, this kind of term ramification. Why does it interfere here with THH? And it's very easy actually. So the proof for the THH case, we have a formula for THH of B using the construction of the root adjunction and just juggling somehow the cyclic bar construction, you get a formula telling you that you have such a formula. And then if you want to look at the degree 0 part, well, this part is in degree 0. And you'll just be taking the degree 0 part here. So you are left to showing that this guy, when you map it to this guy, well, this one. Oops, this was not a good idea. This is in degree 0, so it will land in the degree 0 part, and then you want here to have an equivalence. And if you have this, then this will cancel out, and you will get the formula you wanted, right? Yeah.
So what does P actually do here? Are we completing at P? Or
Yeah. Sorry, I forgot to say, but of course, for now on, P is a chosen prime. Everything is P local. Thank you. Yeah. everything is p-local. I mean A and then of course B are p-local. Yep. So this map that you have up here, well, on the E2 page of the HZ Bergstedt spectral sequence, the map above reads, well, it's pretty easy. You have just and then an exterior algebra. And it maps to something similar. And then here, sigma km and G is to map to okay. So if P is prime to M, then this is going to be an isomorphism. Okay, and then I mean for the other part, well, you use the fact that it equivariantly splits into into disgraded pieces. So that's a story for root adjunction on THH in the tamely ramified case, if you want. So what about TC and K-theory? So for TC, okay, it's a bit different. So, well, we have seen already several times TC on the blackboard. Maybe I'll just still write it out for you once. And here you have this map to well, depend of. I prefer to emphasize that map, so I prefer to write here THH. Like this. And so we have seen that here this splits. This splits. And we have that can preserves splitting, but not phi p. That's also proven by Thomas Nikolaus and his co-author.
Can you say something about what a so-called algebraic spectrum is, because you're doing all these constructions?
Yeah, no, I didn't really say. So you have well, you take functors from the discrete Z mod M, so no, just a zero category if you want, into the symmetric monoidal category of spectra, and then you take En algebras that category. So that's a symmetric monoidal category with the deconvolution product, and you take algebras in there. So it's not a grading in an algebra which would be somehow square zero or these kind of things. I mean, it doesn't split as algebras.
All these constructions that take construction homotopy fixed points, they're just
Yeah.
on the underlying.
Yeah. I mean, those is splitting are as modules if you want. Yeah. So they show that if I look at the east part of THH of B, well, this phi will take it to P times I, okay? So in fact, you don't really get here a priori a splitting of TC. So the second theorem that we have here now R is connective. And P is again prime to M. Then again this J map split as a spectrum map, okay? And B, if K is positive, K was the degree of the root that you have adjoined. This also splits, okay? Okay. Do I have time to indicate a proof, maybe briefly? Oops. So here we just observe somehow that that P is not a zero divisor in Z mod M, so that somehow the Frobenius is going to take the zeroth part to the zeroth part and the non-zero part to the non-zero part, without respecting the grading on the non-zero part. And that's it, basically, right? 0. So since all the rest was splitting, you also get your splitting. Okay, so that's easy somehow now. And for B, it's also using a powerful theorem of Dundas, Goodwillie-McCarthy. Well, we look at the so yeah, the condition on K says that they have the same pi 0. And here, well, the splitting that we have is something like this. And if we forget this part and put here A, we have our fiber square. So if we add this part, we will have actually just the splitting of the K-theory of B. So this gives us the formula. Okay. That's all pretty elementary and not too many computations. So a corollary. In the situation above, if A is not connective, we're going to have that for E larger or equal to 2. So this is somehow, here we want to compare the connective cover to apply the theorem 2. And when we pass to connective cover, we're going to have equivalences on TI localization starting with 1, and then using purity, we'll get to this corollary. So that's somehow useful to say that if you know that, for example, this doesn't vanish, then you automatically get the non-vanishing on that side. And often the non-vanishing now is what remains of improving redshift. It remains to prove non-vanishing results, at least in a commutative case. And we can use this corollary to try and deduce non-vanishing results. Okay, another remark maybe. Also, a quite elementary observation is that if you look at what the map, Frobenius map does up here, of course, if P is congruent to 1 modulo M, then it respects the grading. So if respect the grading, and therefore TC and K-theory will inherit a grading. Okay, so Özgür, yeah, maybe I'll write it after. So let's look at some examples now. So first we cover the baby example. In an E1 version, if you want. And but also here we have we are in the case where P is congruent to 1 modulo M. Remember, we were joining a P minus 1 root of V1. So you have actually that TC and K-theory are going to split. And with this, Özgür makes a simplified computation of, let's say, T2. Okay, so yeah, that's somehow the things we were looking after, knowing knowing this guy, could we just deduce this somehow by some formal manipulation? And now that's the case with this result, if you want. So that's quite nice. We can do also the uninteresting case of real K-theory. If you look at real K-theory, well, its coefficient, it's just a polynomial algebra on a class in degree 4. Right, if you look at the real Bott periodicity, you have the two torsion and then and that guy. And then you can show also that you have some nice root adjunction here. We have in the setting above that this is obtained from L by adjoining P minus 1 over 2, root of V1, okay? But also Ku is obtained from Ko. So you have some intermediary, if you want, extension between L and Ku. And here also, P is congruent to 1 modulo 2. So we are going actually to have K-theory splittings here also. Okay, so with this, we have a formula for T2. Okay. So you can write completely what the classes are and so on. So we have a nice formula for T2 of KOP. Just falling out. Some other examples. We can also start with BPN. And adjoin a Pn minus 1 root of Vn in here. So if we Kn localize that, we obtain a form of a Lubin-Tate spectrum over Fp, well, over the p-adic. So that's essentially due to Hesselholt and Stragowski that we can identify then this with adjunction. So by the corollary, then we will get that LTN LTN plus 1. K-theory of okay, and in the n equal 2 case, well, with Gabriel, Angelini, Noll, Dominique Culver, Eva Höning, John Rognes, we have a computation of V2 of this guy or of LT3 of this guy. So we have a big chunk that is going to be present in the K-theory of this these universal deformations. And Hahn, Jeremy Hahn also, and also in discussion with Robert Björklund, indicated us how we might also reprove Yuan's theorem. Is that if you want to pass here to a genuine Lubin-Tate, the ordinary Lubin-Tate spectrum, you could start with extending, in some sense, pi 0 to the Witt vectors over Fpn. And then adjoining the root and localizing, you will recover a Lubin-Tate spectrum. And then you can somehow prove along the line of Hahn-Wilson that the K-theory of this guy doesn't vanish, so you will deduce that the K-theory of this guy doesn't vanish, which is also nice. Okay. And finally, I somewhat skipped the log part, but we also have a nice, or at least an easy formula for a log version of THH. So maybe I'll just write this in a remark. So this setting also allows for a definition of log THH and splitting results so somehow it's a relatively easy formula. If you want to define in the situation that we have, somehow you have a class in this evenly graded E2 algebra, and you want to somehow add the Cayley differential dA over A. Well, you can define this as THH of A. We smash over THH so now you take somehow the Laurent polynomial algebra. So here, if you want THH, is going to be again polynomial on that guy, and if you want the Cayley differential, I mean Laurent series tensor the Cayley differential, so you can divide the Cayley differential up to whatever you want. But if you just take the positive degree part, you will just be left with the Cayley differential d sigma km divided by sigma km once, and that's a nice formula from which you can also construct a localization sequence and corresponding splitting for log THH. Well, thank you. That's all I wanted to say. Yeah.
So you pointed out that the choice of this map from the S sigma K hitting A, there's no unique choice. Is there? Well, you presented all the computations not depending on this choice. Is there anything that lets you identify different choices for this, or any invariant that sees this?
No, I don't. I mean, in some sense, sometimes you have like uniqueness results, and essentially if you have this type of, like for the L case, L and KU case, essentially you fall back on KU because of some uniqueness, but otherwise I don't see how to point a particularly map.
So for different choices, this could silently be different spectra that happen to have the same THH all the time.
Yeah.
I mean, they would have different E1 structure.
They have different E1, but in the end we just remain with the module structure, and I'm not sure. Yeah.
Maybe a related question, can one not E1 present that kind of thing where you adjoin a piece root? I mean, what I have in mind, you start with your spectrum and you adjoin a piece root as an E1 generator, and then you sort of need to identify that, and then there should be some sort of a Massey product in degree, whatever, the new guy times the piece root minus 1, and then somehow I would expect you have a countable like sort of number of higher Massey products to kill.
Yeah, to identify two versions, you mean? Or?
I mean, just to present it as an E1 algebra, and you see exactly what are sort of in the end the choices.
Yeah.
Have you thought about such a presentation?
No. I mean, I mean, obviously, when you use this cellular, when you choose a cellular structure, you are going to choose homotopies to be extending over the cellular, and so maybe we can. It will be interesting to pursue that. Yeah.
Anything you can do if P divides N?
I don't know. I mean, you can define the root adjunction, but as far as splitting, I don't know how that this widely ramified case.